All right. Um, Last time we've talked first about bilinear and then about multilinear maps. Quickly, just to go over the what we discussed last lecture again. Bilinear maps are consist of essentially three groups: G1, G2, G3, all isomorphic to ZP, but they should be cryptographic groups. That is, the discrete logarithm problem should be hard in these groups uh, as a minimum. And additionally, we have such a bilinear map, which maps from G1 times G2 to G3, which essentially lets us do a multiplication in the exponent. And the reason this was originally proposed by Antoine was to build something called three-party key exchange. So three parties, Alice, Bob, and Charlie, just release a, let's call it a public key. Alice is the encoding of A, Bob the encoding of B, and Charlie the encoding of C. And now these three parties can, without any further interaction, establish a joint key. Just this encoding of, oops, no, 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 no. Okay, anyway, I'm gonna fix this later. Okay, oh, good, I think it's fixed. This encoding of ABC. Okay, now this was back in 2001. In 2013, there was another essentially breakthrough when these first multilinear maps were these first candidates of multilinear maps were proposed by Garg, Gentry, and Halevi. So while bilinear maps allow us to perform multiplication between two fixed groups and nothing else, right? I can do a single multiplication that I'm in this group G3. In the multilinear setting, I have a whole family of groups, right? So I first fix a universe U. Let's just say that's the numbers from 1 to n. And then for each subset S in this universe, I'm gonna have a group GS. And every single one of these groups is isomorphic to ZP. And we denote the encoding of a ZP element X in this group GS as square brackets of S of X index S. So now GS is a group in the usual sense. That means we can perform group operations, which we denote additively in this group. So adding elements or taking ZP linear combination does the expected thing. But then of course, what makes these multilinear maps special is that we also have a multiplication between these groups, GS and GT. So let's take ourselves index sets S and T in this universe, such that S intersect T is the empty set. It means S and T are disjoint. This is a very simple legality condition. This just comes, I mean, maybe a bit surprising here or out of nothing, but later this will be very useful. And in fact, the first multilinear maps as proposed by Garg, Gentry, and Halevi did not have this set structure. So the groups were not ordered like in this set family, and they didn't have precisely this legality condition. But for our purposes, what we want to do, these leveled multilinear maps with this legality condition are essentially what we need, as we will see later. Probably not today, but what makes these multilinear groups now special is that if I have two such legal subsets S and T, I can multiply elements in GS with elements in GT, right? In the canonic way. So my multiplication now takes an element in the group GS, an element in the group GT, and outputs something in the group GS union T, right? And it does the expected thing. If I take a group element encoding X and one encoding Y, I get the group element encoding X times Y in this target group GS union T. That is, this bilinear operation here allows us to multiply elements in compatible groups. So the first application, which was, or essentially the only real application, which was provided in this work by Garg, Gentry, and Halevi, was, well, a generalization of Jou's application. Namely, instead of three-party key exchange, they proposed to do multi-party key exchange. And what's better than three? Well, let's say we have four parties, A, B, C, and D. And for simplicity, I'm forgetting about this leveled structure for this application. As I said, Garg, Gentry, and Halevi did not propose these leveled multilinear maps. But of course, I can do non-leveled multilinear maps with leveled multilinear maps by just having each party publish encodings in on every level. So Alice outputs an element encoding A, where A is uniformly random in ZP, Bob B, Charlie some lowercase c. Let's say Dora has a D. Now, the nice thing about these multilinear maps is that in this setting here, we can these parties can come together and create ad hoc keys, right? Let's say, for instance, Alice, Bob, and Charlie, they each published this first message on their homepage. Now, let's say Alice wants to broadcast something, or let's say Alice, Bob, Charlie, and Dora. Alice wants to broadcast something to this group. What can she do now? Well, she can take this A, B. She can compute A times, well, B times C times D, right? And if we really think about the most simple level structure, which just counts the number of multiplications, that's what they did. So then we have two multiplications in these in these multilinear groups happening here. So we are ending up, so to speak, on a third level with this. And now she can set this key here, right? Ending up in, let's maybe call this group G3. The observation is that anyone who just sees the public information, namely encoding of or group element of A, B, C, and D, an adversary can only compute like A times B times C times D, and this would now be on a fourth level, right? Let's say in a group G4. So with public information, you will not manage to produce this this element, which is of course A, B, C, D, on level 3, right? You will only be able to do this like in the fourth group. So these 4 parties can create this key in level 3 and then use it to encrypt messages, right? And would of course be amazing for let's say instant group messaging in some instant messaging service where you can form an ad hoc group with these other people, Alice with Bob, Charlie, and Dora, without ever having talked to them before. So you just pull their public key from their homepage or whatever profile in WhatsApp and start an encrypted conversation without having to wait for them to acknowledge that you want to start an encrypted group chat, right? As it would be the case if we were just using like 2 or 3 party key exchange. So that was the new envisioned application of multilinear maps, this non-interactive multi-party key exchange. Okay, but as I already alluded to last times, there are a few side notes. So GGH13 did not construct exact multilinear maps. So in particular, what is reflected there is the kind of structure that they had. These groups GS, they were actually not really groups. They were something like a group with an error. So you can do additions in this group, but you have errors that pile up in fact, very, very similar way as this is the case in the construction of fully homomorphic encryption that we have seen, right? In the GSW construction, we also had that each ciphertext had an error, and these errors are piling up somehow. And there needs to be a mechanism to control these errors or to keep them from growing too much. So what they really had was some kind of an approximate multilinear map with errors from a structure called ideal lattices. So I'm not going to go into this. I mean, I can post some links if any of you are interested, but these are special types of lattices that are related to algebraic number fields. So something that's a big deal in math, but here in this lecture, we won't have the time to get into this. Okay, so I said already that this construction is approximate in the sense that group operations introduce an error, and this has the somewhat weird consequence that group elements in their construction do not have a unique representation. So if you just think about modular exponentiation as a homomorphism into a group, then of course every ZP element has a unique representation in this other group. But here in what they were doing, you could have the same ZP element but encoded in different ways. So they had a randomized representation, and a priori, it's not clear whether 2 group elements or 2 such elements in these multilinear groups actually represent the same ZP element. So it was a bit like, or their construction was a bit like fully homomorphic encryption. I mean, as a side note of a side note, they constructed their scheme from their multilinear map scheme from a fully homomorphic encryption scheme. So they took a fully homomorphic encryption scheme and weakened it in a deliberate way, namely by introducing something called a zero testing procedure. So a zero testing procedure, you can think of an operation, a publicly computable operation, which allows anyone to test whether two ciphertexts encrypt the same thing, or whether two group elements encode the same ZP element, right? Of course, if you have anything like that, you can't be in CPA secure anymore. So there was kind of a precarious approach from today's perspective to start with a fully homomorphic encryption scheme, which is secure, which has in CPA security, and to deliberately weaken it in order to enable this zero testing procedures. And they conjectured that introducing this zero test would not make this multilinear group insecure. In particular, it wouldn't make it easy to compute discrete logarithms in this group. This is the minimum assumption which you always want from a cryptographic group. In fact, you want quite a bit more. So it turned out that this, we're going to go later into this, not today, that this was a bit of a problematic approach. So this whole paradigm of starting with a fully homomorphic encryption scheme and deliberately weakening it was in this sense by providing this all-purpose zero test. This was a bit of a problematic approach. Okay, but this finishes the slides from last time. Now let's go to today's lecture, already 17 minutes in. Namely, today we will talk about branching program obfuscation. Okay, now we have this tool of multilinear maps. Now we want to do obfuscation with it. So first thing is that the standard model of computation in theoretical computer science, Boolean circuits, they can express arbitrary computations. Arbitrary computations, of course, of a fixed size. But they do that using only elementary gates. So one might think that this is a fairly simple model of computation. But, well, if you look at this, it's not just the gates. You need to have wires between these gates, and that introduces or can introduce a quite complex topology, right? So circuits sort of or Boolean circuits can work using very simple gates. You can do everything just using NAND gates, but the wiring of these circuits, that's sort of where all the sophistication of the circuit goes into. And what makes these circuits actually a bit of a complex structure, right? They have a complex structure and complex topology, how the wiring is. And if we wanted to start just obfuscating circuits, give me a circuit and do some transformation on this circuit directly. People have tried this, but it turns out this makes these constructions really hard to analyze. So in a sense, even though Boolean circuits are a simple model of computation, well, compared to Turing machines or random access machines, they still carry a lot of structure, which makes it hard to analyze obfuscation candidates on this in this model of computation. So we really need a simpler model of computation, which in some sense should facilitate analyzing the effects of program transformations, right? Sort of introducing dummy gates here. Well, in a circuit, why should that be any good? Why should whatever be any good? So we really we need an even simpler model of computation where sort of we can apply natural algebraic transformations and analyze their effect. Right, so for everything we do in an obfuscator, we want to have a good reason why we would want to do this. And on the circuit level, that's just typically not given. Okay, therefore, we start today by talking about matrix branching programs. So what's a matrix branching program? So that's such a program P of length L for input space 0, 1 to the n. So such a program takes inputs from 0, 1 to the n. This is just given by a list of matrices Si, comma b. So for every index I in L and bit b in 0, 1, you're having a matrix SIB. So in the end, you have two L matrices here, where each of these matrices SIB is in ZQ to the W times W. Q can be any integer, but it's probably easiest to think of it as a prime, small or large, can in fact be anything, and W as probably just a constant size integer, something like 7, 8, 9. Don't think as of W as big, but that's the first part, these 2n matrices. And additionally, we have a input mapping function, which takes an input map, which takes an index between 1 and L and maps it to some index between 1 and n. So here for this input mapping function, you can in fact just give me the entire function table, right? Don't think of this int function to do any complex computation. Just think of this as being given as a kind of a wiring function, as a function table, because it's really a small function. It has a small input set and a small output set. So there's not too many of these functions. So now, given such a branching program specified by these matrices SIB and this input map imp, how do we actually evaluate such branching programs? Well, let's take an input x in 0, 1 to the n. What we do is we just compute the product of the matrices Si, x imp I. So I'm gonna make a drawing on the next slide to just visualize for you how this evaluation procedure works. But one thing here, if once we computed this y, if y equals the identity matrix, then we interpret the output of this branching program on input x as 0. Otherwise, if y is anything different from the identity matrix, we interpret the output as 1. And here we will call W the width of the branching program. I'm gonna comment on that in just a bit. But let's first maybe see how this works. So a branching program, we have it given by matrices S10, S11, S20, and S21, and so forth until let's maybe even make it more concrete. Let's make a branching program of some S30 and S31, S40, and S4, 1, right? Those are all square matrices from ZQ to the W times W. So even though my drawing is a little bit off, they are all matrices of the same size. And well, how do we evaluate such a branching program? Well, the second thing that's missing is an input, this input mapping. And the way I'm gonna draw this input mapping for this program P is just by I'm saying, well, at the first position, I'm taking x1, so I'm mapping 1 to 1. At the second position, let's say here I'm taking x3, then here I'm taking x1 again, and here x2. Okay, so this input function tells me that on the when I will choose the first matrix, the bit the bit I should look at is x1. So here my imp function is really just given 1 maps to 1, 2 maps to 3, 3 maps to 1, and 4 maps to 2. That's my input function. And now, how do I evaluate such a branching program, say on input x equals 0, 0, 1, right? x1 is 0, x2 is 0, and x3 is 1. Well, I first go here. x1 is 0, that means I need to take the matrix S1, 0. So I'm taking this matrix here. Now I'm going to go to the second position, x3. x3 is 1, so I have to take this guy here. Now here again, x1, we know x1 is 0, so I have to take the S3, 0, and x2 is also 0. I multiply, and finally I just multiply all these matrices together, right? So in this case, I just have y equals S1, 0 times S2, 1 times S3, 0 times S4, 1. And now I just have to test whether y is the identity matrix. If y is the identity matrix, so if y equals I, then output 0, put 0, otherwise 1. So this is, in some sense, a fairly simple model of computation, right? So the input just specifies for each position in this branching program here, if I should take the upper matrix, that's if xi is 0, or the lower matrix if xi is 1. Then in the end, just multiply everything together. And if you look at this, you wouldn't, when you evaluate a program, such a branching program, you wouldn't do it like this. You wouldn't first go through all the indices and look which matrix you need, and then in the end compute the product. No, you can do that on the fly, right? So you start with the first position. So this is S1, 0. Then second position, so there you have S2, 1. And now you multiply this matrix S2, 1 directly on top and remember the result, right? Now you go to the next position. There you have S3, 0. Also multiply that on top, and last S4, 0. So you can really compute these branching programs in sort of a streaming fashion. Wait, there was a S40. Thanks. So someone, I saw where the error, the typo 4, 0. Okay, good. That means people are paying attention. Great. Is there so far any question to this computational model of branching programs? I mean, I'm still going to talk a bit about this, but so far just in terms of evaluation, and we will talk a bit more about examples, but is there so far any question regarding this? I guess if not, let's just continue. And first thing which we will need is the notion of an oblivious matrix branching program. So we say that a construction means an entire family of branching programs is oblivious if this function imp doesn't really depend on the program itself, but only on the program length L. Right? So this notion of oblivious branching program doesn't make sense for just a single branching program, but it should be an entire family of them. It should be like 200 programs that all use the same imp function. Right? And then for such a construction of branching program, imp doesn't depend on the specific program P that you're computing, but just on its length L. i.e., imp is really the same for all such branching programs of length L. And the great thing here is that for such oblivious matrix branching programs, imp does not leak information about P beyond its size. And if we remember what we're trying to do here, this is great for obfuscation, right? When we obfuscate programs, we would really like to leak as little information as possible about the program which we're obfuscating. And now if for such an oblivious branching program, this function imp is always the same, therefore doesn't leak anything about the program beyond its size. Recall, the size of a program is something that an obfuscator can't hide. Then this is great for us, right? One thing less to worry about. We don't have to worry about this imp function, or which essentially specifies the order in which we read the input, that this could leak something. So we really only have to look at the matrices when we at these matrices SIB when we obfuscate stuff. So a nice thing about branching programs and oblivious branching programs is we can really achieve that in an almost trivial way, just by sort of filling up a branching program. So let's say we have a now let's use the other color. Oops, no. So let's say we have a branching program, let's say of length 3, right? We have S10, S11, S20, and S2, 1, and finally S30 and S31. Let's say this branching program P starts by reading the input x2. It just takes 2 bits, right? P is just defined on 0, 1 to the 2. Then it takes x1. And then here it takes x2 again, right? So I've showed you how to evaluate these things. Now let's see how to bring such a branching program into a somewhat canonical form. So I really want that this sequence x2, x1, x2, that this doesn't leak anything about my program. And the way I'm doing this will be just for each input or for each input in this program, for each position in this program, I am sort of gonna read all the inputs. Right, so here instead of just reading x2, I will read both x1 and x2. Right, I will have to do something with x1 and x2. So here, second, there, I will also have to read x1 and x2. In fact, this program does this already. If I let's say here I'm having the third one, so let's make that instead of reading x2, I'm really also reading x1 and x2. So I've taken this program of length L, here L equal 3, and now I have n times L is 2 times 3 is length 6. Okay, so what do I do? My original program P, here I have P prime, that's my oblivious program. The original program was reading x2 first. The oblivious program is supposed to read x1 first. So really, what I'm gonna do is I'm including a dummy operation here. Right? So for these branching programs, including dummy operations is actually already a meaningful transformation that achieves a meaningful goal, namely making the branching program oblivious, in the sense that this input function doesn't leak anything about the original program. And how do I introduce dummy operations? Well, just by putting the identity matrix here, right? Multiplying any matrix with the identity matrix doesn't change anything. For x2, I leave things how they were. Here I still have this matrix S10, S11. Now here, I leave things how they were, S2, 0 and S2, 1. Here, x2 is not supposed to be read in the second step, so I'm also introducing a dummy operation here. And the identity. Further here, now x1 is not supposed to be read in the third step, so I'm also gonna introduce a dummy operation here. And finally, S3, 0 and S3, 1. Right? And we can immediately see wherever I've introduced these dummy operations, that will not affect the evaluation of this branching program P prime. So P prime still computes the same function as P, but is now oblivious in the sense that the pattern in which I access my inputs does not depend on the original program P. Right? I started with a program that first reads x2, then x1, then x2 again. Now this one here really has a very simple access pattern: x1, x2, x1, x2, x1, x2. Right? So and this is really a simple transformation, and I can always achieve this in this way. If I have n input bits, I just blow up the original program by a factor of n by essentially just introducing a lot of dummy operations, right? In this way, such that in each block of inputs, I nominally read all of them, x1, x2, but of course, most of these will now be dummy operations. Are there any questions so far regarding branching programs and oblivious branching programs? Okay. So I guess this notion. Yes.
Maybe one small. So it's completely. So you can't distinguish from the outside these identity operations from the.
No, you can. You can. I'm just presenting this program, right? Instead of having these matrices for the program P, I'm gonna give you the program P prime. So these matrices, you can when I give you the entire program P prime, you can easily distinguish it, right, from something else, because now you have the identity matrices there. Right? These are really just CP matrices. They're not encoded, encrypted, whatever. They're really just plain matrices. So really the only purpose of this transformation is to make it so that the pattern in which I read the inputs, right? First x1, then x2, first x1, then x2, first x1, then x2, that this access pattern doesn't leak anything about the original program. The matrices themselves, they essentially they may leak everything about the original program.
Okay.
So you're addressing something very good. I will discuss this in a moment. So, but the first question is, now that we have this computational model of branching programs, how expressive are they actually? What can I compute using those things, right? So we know circuits and Turing machines, they are equivalent. Now, where the size of the circuit, of course, grows with the runtime of the Turing machine, but these things, they actually look pretty dumb, right? You just multiply a few matrices together, and as I said earlier already, matrix branching programs can be evaluated using a memory that only stores a single matrix. So when you walk through the input at each point, you just have to be smart enough to remember a single matrix, then multiply another matrix on top, and go on, right? You can evaluate these things with very little memory. You just have to remember only one matrix at each point. And in that sense, they look pretty similar to finite automata, right? So a finite automaton reads an input string, and deciding for each bit of the input string, it goes into another state. And such a state change can actually be modeled via matrix multiplication. So my question here is, do the things actually, are they the same as finite automata? Sort of, are we just, are branching programs just finite automata in disguise? That would be bad, right? Finite automata are, as we all learned, not very expressive in terms of their computational power. They can detect regular languages, right? They cannot even recognize parenthesis languages. I mean, those are context-free languages, right? They really, you cannot, using a finite automaton, you cannot even parse C code or Python code or whatnot. You name it. Not powerful enough. So are these matrix branching programs just finite automata in disguise? The answer is no. Why is the answer no? Any guesses? Okay, so for time reason, I'm just gonna tell you. Well, finite automata can only read their input once, right? A finite automaton gets an input string x1, x2, x3, x4, and each of these input bits can only be read once. you read this input bit or symbol, you perform an operation, and then this input symbol is gone. But for branching programs, as we've just seen, they can read each input bit several times, right? In fact, a polynomial number of times. So that's the difference between branching programs and finite automata. And that's what can give you hope that this model of computation is actually more powerful than just plain old finite automata. Yeah, branching programs can read each input bit many times. But now the question is, okay, they seem to be more powerful than finite automata, but what class of functions can we hope to compute with branching programs? This already leads us now to Barrington's theorem, which we're gonna go into. This theorem says that if I have a function f going from 0, 1 to the n to 0, 1, if this can be computed by a Boolean circuit of depth d, then it can be computed as well by a branching program over ZQ for any integer u greater or equal to of width 5. So I just have 5 times 5 matrices, but of length 4 to the d. Okay, so if I'm starting with a circuit of depth d, I'm gonna get a branching program of depth exponential in d. Is this horrible? Is this horrible that if I start with a circuit of depth d, then I get a branching program of depth d?
I mean, it's about the same amounts of operation, right? Because in a circuit of depth d,
Yeah.
you can have 2 to the d operations.
Yes, but you could have a circuit which is of size, let's say, n, and just does n sequential operations, right? So you would turn sort of a sequential sequential computation into something exponentially large. So maybe I'll just go ahead and say, if we start with a circuit which has depth at most logarithmic, then this circuit can be equivalently computed by a branching program of polynomial size. Right? So if d is of the order log n, then 4 to the d is some polynomial in n. Okay, so logarithmic depth circuits are translated into polynomial size, that is, small branching programs. Okay, so in fact, Barrington theorem is, the way it was provided by Barrington, is an equivalence. It states that those two classes of programs, on one hand side, circuits of depth log n, on the other hand, branching programs of polynomial size, they are equivalent. You can always translate one into the other. So the part that does not interest us today is that every branching program of polynomial size can be simulated by a circuit of depth log n. So this is the reverse direction of Barrington theorem, but we're only interested in converting circuits into branching programs. Specifically, this class of circuits of depth 1, is in complexity lingo called NC1. That is a Nick's class of order 1. There's, of course, also an NC0. Those are circuits of constant depth. There's NC2. They are circuits of depth log n square and so forth. But the one that we're interested now is NC1, named after Nick Pippenger. So NC really just stands for Nick's class. And still, right? So I was asking earlier, how expressive are branching programs? And now this theorem comes and tells us that they are as expressive as these log depth or shallow circuits. So, I mean, this has just shifted the problem, right? In a way, now I'm not talking about branching programs, but about these shallow circuits. Are these shallow circuits any useful? And it turns out, yes, they're incredibly useful. They can do almost all you would wish to do in cryptography. There's a few things you cannot do in low depth, but there's really many interesting functions in there, such as exponentiations in elliptic curves. You would maybe first think that's a highly sequential operation, but no, you can really do that in a very shallow way. Matrix multiplications, rounding, and therefore encryption and decryption, for instance, for the GSW scheme, right? So in a way, NC1 captures all the functions which are in some sense highly parallelizable. So if you can compute something with a circuit that is of low depth, that means you need to go into the width, right? You need to be very parallel. So NC1 kind of captures all the problems which really lend themselves to parallelization. And it turns out really a lot of things that we do in crypto can be highly parallelized, right? A lot of encryption and decryption operations can be parallelized and are therefore in this class NC1. Any questions? Okay. Then let's quickly look into the proof. How does this work? So now the idea is, of course, simulate a NC1 circuit via a branching program. And the way I'm gonna do this proof is I'm gonna do this recursively or inductively. Proof works inductively. Let's say I'm having a circuit C, right, which is composed of two smaller circuits. Namely, let's say on the top level, I just have an AND gate, and underneath this input here is computed by a circuit C1, and this one here by a circuit C2, right? So I'm really just looking at the top gate, and then later I'm gonna repeat the same thing for these smaller circuits C1 and C2. Now we know that AND gates cannot represent, or using just AND gates, I cannot compute all possible functions. So I need to look at a second setting. Namely, I need at least one extra gate, and what I'm using there is just a negation gate, right? And now I have that AND and negation. Well, that gives me NAND. We all know that I can express any circuit using just a NAND gate. Okay, so I'm doing this inductively. In both cases, I assume that, well, C1 and C2, they're smaller circuits. So I assume they can be computed by a branching program of polynomial size. And then I'm going to show that why am I calling this C2? 1 second, it shouldn't be C2. Then the one I'm having here can also be computed by a branching program of polynomial size. I hope I have enough. Yeah, I have enough extra slides and or enough extra space here. Yeah, good. So let's maybe first look at the second case that we want to compute a negation. Okay, what I'm using here is I'm just using very simple 5 times 5 matrices, right? So all my matrices S I comma B are some, let's maybe draw them 5 times 5 matrices, and I'm gonna choose them such that in every row and every column only a single one per row and only a single one per column. Okay, so my matrices, they look really simple. I'm not gonna use the full power of these matrix branching programs. In fact, Barrington calls this a permutation branching program. Okay, so for us, it will be, for our application, for obfuscation, it will be easier to think about these things as matrices. But as a matter of fact, those things that we need here are just permutations. So if you give me such an SIB, basically what they do is if you multiply a vector with this matrices, row or column wise, they just permute the coordinates. Okay, so these matrices represent symmetric group S5, right? S5, that's the set of all permutations on 5 elements. So really, these matrices just permute coordinates, so we can likewise think of them as permutations, right? So each matrix here just computes a permutation, and this group of permutations of a set of size 5 is just called the S5, the symmetric group S5. Okay, and now I'm just I'm gonna import a few little things from group theory. They're not hard to establish, but anyway, I don't want to spend time on this. So if you think about the following matrix, let's say it takes 1 maps it to 2, it takes 2 maps it to 3, 3 maps it. Oh, by the way, this is only 4 elements, so let's maybe make one extra there. So 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 1. So this is essentially just a cycle permutation, right? And the corresponding permutation we sometimes, I hope you've seen this, we write as 1, 2, 3, 4, 5. It maps 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 1. It's a cycle of length 5. So what I am gonna do is I will encode the output 0 as before, just by the identity permutation. The permutation, I mean, we call that it, right, which maps everything to itself. And I will encode a output 1 by this cycle permutation. Right, and it is just really the diagonal, the identity matrix in diagonal. So essentially the only or two things I'm going to import now from group theory is there are two cycle permutations. Let's call them sigma comma tau in S5, right? In the symmetric group S5, such that sigma times tau times sigma inverse times tau inverse is again a cycle permutation. Okay, what I have here, the sigma I had defined up here is just the most basic cycle. But you could also a cycle could also be of the form 1 maps to 3, 3 maps to 5, 5 maps to 2, 2 maps to 4, and 4 maps to 1 again. So these cycles can look differently. But basically, what these cycle permutations have in common is that if I apply this cycle permutation 5 times, one after in 5 times in a row, I will get the identity permutation, and 5 is in fact the smallest number that's needed to do that, right? So 5 is the order of the subgroup of this generated by this cycle, right? We've seen stuff like that before. And group theory, this is fact 1. I just need a second fact, fact 2. It's just if I have sigma tau are cycles. Come on. Cycle perms. Then there exists a permutation pi, not necessarily cycle. Cycle such that sigma is equal pi times tau times pi inverse, right? I can obtain sigma by just conjugating tau with this permutation pi. In fact, these conjugation operation, right, multiplying from the left with some permutation pi, from the right side with pi inverse, those are in fact the group homomorphisms. In fact, the only group, the group automorphisms that I have in this group S5. So I can, in a way, there's an every cycle is sort of the image of another cycle under an automorphism. Okay, it means I mean, what this means for us, if I again have sigma being this let's say standard cycle 1, 2, 3, 4, 5, I can map any cycle tau back to sigma just by multiplying it from the right side with some pi inverse, from the left side with some pi. Okay, but good. Now that we have this group theory stuff out of the way, let's say we have a branching program which computes a let's call that C, and we want to compute not C, right, or next C. We want to compute a negation. So what can I do with a branching program to, or let's say here I have a circuit C which computes something. This circuit C corresponds to a branching program P. What do I have to do to compute this circuit? If P computes C, what do I have to do to compute not C? Any ideas? What could I do with this branching program? How could I transform it? Okay, I'm just going to tell you. What I'm going to do is, instead of computing P itself, I'm just going to add one additional, let's say, dummy input. This could be x1, right? And for x1, I'm just so I'm adding an extra row here to this, sorry, extra column to this branching program. And what I'm computing here is just sigma inverse and also sigma inverse. So what this program computes is just P of x times sigma inverse. Okay, now I have the claim that this program computes the negation of whatever P computed. This is not quite there yet, but we'll see. This is almost there. So if you think about it, what if P of x equals if C of x? Let's make it this way. If I have C of x equals 0, then I know that P of x equals the identity, right? Identity encodes a 0. Therefore, I have P of x times sigma inverse is just sigma inverse, the inverse cycle of 1, 2, 3, 4, 5. On the other hand, if I have C of x equals 1, C of x equals 1, then I have P of x equals sigma, and therefore P of x times sigma inverse equals identity. Great. So the second one is already good, right? Because if C of x equals 1 and I negate that, it should be 0. And the identity permutation exactly encodes 0. But I mean, on the first row, I'm not quite done yet. I would like to have not sigma inverse there, but sigma. What do I do? Any idea? How do I turn a sigma inverse into a sigma? Well, what I'm going to use is this thing up here. This says I can do this for any cycles sigma and tau. So obviously sigma is a 5 cycle, but also sigma inverse is a 5 cycle. So I know that now maybe a bit bad in space, but here I know that there exists a pi such that sigma is equal pi times sigma inverse times pi inverse. Okay, and with that I essentially have it. So what I need to do now, how do I really transform my branching program? I'm starting with P, and I'm gonna map this into one that first, let's say on an input x1, it just multiplies pi, then it does whatever P did, right? Then does the branching program P. Now again, let's say x1, it computes this sigma inverse, and then let's just say again x1, but this can be anything, right? Because this is constant pi inverse, and that's it.
Sorry, one question.
Yeah.
Is there maybe an inverse missing at the top, in the such that
no.
a pi?
I mean pi times tau times pi inverse. It just says there exists a permutation pi that sort of translates between sigma and tau.
Oh, okay. So you can just kind of, or you can infer that the same holds to the -1. Okay.
Exactly. No. I'm just setting what I'm doing here is I'm setting tau equals sigma inverse, right? I'm using this fact to use with tau equals sigma inverse. Oops, it tells me my connection is unstable. Maybe I'm gonna go slow for a moment. Do you all hear me well? Anyone? Just stand up and...
Yes, we can hear you.
So. Okay, good. It just told me that my connection is unstable. Okay, and if we look at the size of this branching program, basically the length increases by, let's use a different color, length increases by 3, right? So when I want to compute a negation, that accounts for a length increase of 3. That is okay. So it doesn't make the, it only increases the size of the branching program additively by 3. So now I need to introduce an extra slide. Let's maybe make already 2. Okay, good. Because I ran out of, I was expecting to write smaller. Okay, now let's look again at this case, at the more interesting case that, let's say our circuit C is just the AND of C1 and C2, right? Now let's say we have a branching program P1 that computes C1 and P2 that computes C2. Now I want to have a branching program that computes P1 or C1 and C2. And how I'm going to define this, P3 will do the following. First, it will compute P1. That's my branching program here, right? Next, it will compute P2, right? I'm just multiplying that here. This is all multiplied in the end into the same matrix, but now I'm computing P1 inverse. I can compute P1 inverse by just taking all the inverse matrices of these PIB and reversing their order. So if I can, obviously, if I can compute, if I have a branching program P, then P in verse, I have a branching program that computes the inverse matrix, and finally P2 inverse, right? And I'm claiming that this computes the AND of P1 and P2. Computes AND of P1 and P2. Right, so I have to make sure that the following, if we can essentially go through the entire function table, if P1 of x equals 0, comma P2 of x equals 0, then P3 of x should be the identity, sorry, not 0, identity. We're already on the branching program level. So, but identity, of course, encodes a 0. Same thing if P1 of x equals identity, P2 of x, let's say, is sigma, then P3 of x should still be identity, right? 0 and 1 is still 0. Again, if P1 of x is sigma, P2 of x equals identity, then again, P3 of x should be identity. And finally, if P1 of x equals sigma and P2 of x equals sigma, then P3 of x should also be sigma. Okay, that's what I have to look into. But now let's look into P3. So I have P3 of x is P1 of x times P2 of x times P1 inverse of x times P2 inverse of x. Right, let's first say P1 is, let's say case 1, P1 of x is equal identity. Then, I mean, I have an identity here. Identity inverse is still identity. I have P3 of x is just P2 of x. That can be non-identity, but times P2 inverse of x. Right? Something times the inverse permutation of itself is just the identity. Great. Same thing happens if P2 of x equals identity, right? Then I just have P3 of x equals P1 of x times P1 of x, P1 inverse of x. This is again identity. Okay. Now the final case, which we'll see is if we were to just do it in this naive way, would be problematic. But if we were just to multiply sigma, let's say case 3, attempt 1, they would have sigma times sigma times sigma inverse times sigma inverse. This is obviously identity. And that's not equal sigma. That's a problem, right? So the this basic idea doesn't work. However, if we go back 3 slides, we have this fact 1, right, which says that there are 2 cycle permutations, sigma and tau. Let's just say sigma is this sigma here, such that sigma times sigma inverse times tau inverse is again a cycle permutation. Okay. And then there's the second fact that I can turn sigma into tau or tau into sigma equivalently. So, wait. Okay, I have to introduce yet another slide, but then I should be good. Okay, so what I'm gonna do is, that's not the color I want. What I'm gonna do is choose pi, let's call it pi 1, such that pi 1 times sigma times pi 1 inverse equals tau, and choose pi 2 such that I have pi 2 times, well, here I have sigma times tau times sigma inverse times tau inverse. I know that this is a cycle, right? By this fact, by fact 1 times pi 2 inverse. This should now just be sigma. Okay, and now I'm gonna define my P3 as follows. Define P3 by, well, so P3 is, first I need to do a pi 2, no matter what the input bit here is. This is just constant. Then I'm computing P1. Instead of P2, I am computing this pi 1 times P2. Here's my P2. Now I have pi 1 inverse and pi 1 inverse. Okay, that's the first part. Then next I have P1 inverse. And now I need to have this conjugated P2 inverse, and that is just pi 1, P2 inverse. I'm running out of space, and pi 1 inverse, pi 1 inverse, and now I just have to close with these pi 2 inverses. Good. And now we will see as before, right? If I go back 2 slides, if either P1 of X equals identity, let's use that with a different color. I'm already running out of time. If say if this is equals id, right? Then this is equals it as well. But now I have pi 2. Then this is identity, exactly. So then I can go here. Then I have pi1 inverse times pi1. This is also identity here. I have pi2 inverse or pi2 times pi2 inverse, also identity. And last things, the pi1s cancel out and the pi2 cancel out. So if p1 of x is identity, then the whole thing is identity. The same thing if p2 of x equals identity. So the interesting case happens if p1 of x equals sigma and p2 of x equals sigma. In that case, I can just write down what p3 is. P3 of x is now pi2 times p1 of x. We know p1 of x is sigma times pi1 times p2 of x is also sigma times pi inverse times, now p1 inverse is sigma inverse times pi1 times, again, sigma inverse times pi1 inverse times pi2 inverse. And now I'm really just using this fact that this thing here, that's a that this thing here is again just sigma times tau, and on the other hand side here, this is just sigma times tau. Sorry, no, it shouldn't be sigma. It should be sigma times tau. Sigma times tau, sigma inverse times tau inverse. Exactly. And what I have here is pi2 times sigma times tau times sigma inverse times tau inverse times pi2 inverse. And by this thing up here, I get that this term is just sigma, as I wanted. Okay, this concludes the proof. And I wanted to at least get here. The first question one could ask oneself is, are branching programs already obfuscation? So when you give me a circuit and I translate it into a branching program via Barrington theorem, is that maybe already an obfuscator? So the answer to that is generally no, but there's actually no time anymore today to look into these examples. So we're gonna continue here in the next lecture. We see examples of branching programs that can still easily be or distinguish, or functionally equivalent circuits, such that if we translate them into branching programs, they can still be easily distinguished. Okay, but I'm out of time for today. Thanks, everyone. I can still take questions if needed.
Maybe just one question. Could you maybe give us some links to possible exercises we could do on our own?
Exercises. I can look for something, but let's see. Maybe I'm gonna find something, but I'm gonna write this down. Maybe I'm gonna find something regarding this. You mean now specifically regarding branching programs?
Yeah.
Okay.
Specifically, but maybe also in general, it would be interesting, especially in preparation for the exam, to kind of
I mean, the
I'm
exam,
interested, yeah, but
I thought I said that before, but in the exam, it won't be about, I mean, it's about ideas and understanding, right? I'm not going to say, okay, here's a branching program, please turn that into, or here's a circuit, please turn it into a branching program, right? I mean, Barrington's program, Barrington theorem, I only did because it's really a central result, in fact, in theoretical computer science and even more in theoretical cryptography. It doesn't just come up in obfuscation. This is an incredibly powerful tool. Therefore, I wanted to go through this at least once. But to be honest, from now on, the details of Barrington theorem don't matter anymore, right?
okay.
From now on, it's sufficient for you essentially to know that you can translate a logarithmic depth circuit into a with 5 branching program. Does that make sense?
Yeah.
So this is kind of not stuff, right? It took me more time than expected. This is not stuff for an exam.
Okay.
I mean, I can try to find something, but I wouldn't know what the added value of this could be for you. I mean, it could be interesting for you to maybe just try to implement this in a programming language of your liking, like Python, and really see how this how the workings of this are. But I mean, exercises, there probably are some exercises, but I guess the added value for you won't be.
Yeah. If you already say that it's like not the main point of this lecture, or maybe a bit too complex, then probably not worth.
Look, the thing is, I have to pick a few results where I go a little bit more in depth, right? And it just happened so I, for today's lecture, chose Barrington theorem. But again, I think we can and we should actually maybe make sort of just a Q&A session where you guys prepare questions for me, right? But my planning for the material I still want to cover is already a bit tight. So maybe we need to find some extra slot for this.
Yeah, okay. I think that would be a good idea before the exam.
Yes. Yes.
And
I mean, look, before the exam anyway, right? We're going to do an Ask Me Anything session. And if you want to take the exam, I mean, you did take the advanced public key crypto exam, right? So there we said, okay, this topic, that topic, not, that topic, not, right? We went through everything and crossed out stuff that wouldn't be asked in the exam.
Yeah, that's true.
So, I mean, of course, we're going to do the same here.
Okay.
Right? All right. So, good. Then thanks, everyone, for joining in today. And yeah, I hope to see you once more next week. Last lecture after Christmas. So long.